Welcome everyone, and thank you for joining us for this use case. Please help us reach a wider audience by tweeting and posting about today's event. If you want to use the minutes now before we start, please feel free to check out our ebook. I'm going to post the link in the chat. You can get it for free today via your Kindle device or Kindle app. Now let me introduce our speaker. Andreas Kopp is Digital Advisor and AI Practitioner at Microsoft. He advises enterprise customers on planning and implementation of digital transformation processes. He specializes in practical solutions for the responsible use of AI. For example, AI interpretability and fairness, as well as differential privacy. I think it's safe to say that the COVID-19 pandemic demonstrates the tremendous importance of data for research, cause analysis, governmental actions, and medical progress, of course. However, for understandable data protection considerations, individuals and decision makers are often very reluctant to share their private or sensitive data. To ensure sustainable progress, we need new practices that enable insights from personal data while reliably protecting individuals' privacy. And this is where Andreas comes into play. Now, one last word. Please feel free to write down questions in the chat at any time. We are going to answer them during the Q&A session at the end. We are recording and use the recording to prepare the proceedings. Also, with permission, some recordings go into YouTube later. And now, without further ado, Andreas, the stage is yours.
Thank you so much, Fabian. So welcome to the session. As Fabian already introduced, this is about differential privacy, which is considered to be the new upcoming gold standard for privacy protection. So the main idea, in a nutshell, the goal is to be able to get general insights about personal data. If you consider a large data set with individual data points, and protecting the privacy of those individuals represented in the data set at the same time for use cases like analytics, but also machine learning and AI. So the idea basically is, for example, we want to do a medical study about the impact of age and a COVID infection, so the severity of a COVID infection. So we want to learn about the general relationship, but we are not interested in the specific data points of John Doe who participated in the study. But what we want to do, we want to provide John with a privacy guarantee so that he is able to join the medical study without any concerns that the data about his condition might be leaked. And the way differential privacy is doing that is by adding random noise to the data. So that's the technical way of protecting privacy, while at the same time still enabling generating insights. So you could argue, well, what's the problem? If we are working with personal data today, there are practices in place like pseudonymization or anonymization. So what's the problem? Why are we talking about a different approach? The problem with current practices is that they are vulnerable to privacy attacks, like we see in more and more real-world threats and also experimental threats. Just two examples here. One is a famous example. It's a research study where researchers have shown that even from an anonymized data set about movie ratings without any PII information, it was possible to actually re-identify the individuals by linking this movie ratings with another public data set, and they did not use any PII information for this linkage attack. They used the movie ratings themselves. And another example, that's actually a real-world privacy attack. You can see on the right-hand side, for those of you who are data science practitioners, probably know the New York taxi dataset. It's quite a famous dataset about taxi rides. There are no PII data included except for the number of passengers. So you have information about the start location, destination location, these kind of things, but nothing what we typically would consider as PII information. But by combining those GPS information with information which attackers found on gossip websites, so paparazzi photos with metadata, it was relatively easy to identify for specific VIPs what was the destination address, how much did they pay for the trip, and did they tip, and how much was the tip. So that's an interesting example that there is no such thing as anonymized data today in reality, because you can pretty much use any kind of information, not what we typically consider as PII, to link this information with other sources and re-identify people from so-called anonymized data sets. And the idea of differential privacy, as I mentioned, is really to protect individual data points while preserving the overall, the big picture on the same time. And here a small shout out to the Facebook PyTorch team. They provided a visual which should help to develop an intuition about the idea of differential privacy. So what you see here are individual data points. You can still see them, and these individual data points, they make up what is called a big picture or overall pattern. In this case, it's the painting of Mona Lisa. And the approach of differential privacy would be to blur, to mask the individual data points so they don't look like this anymore. They look more like this. So the picture on the individual level becomes extremely blurry. You basically see nothing. But the overall big picture, the Mona Lisa, can still be recognized. Actually, there's no big difference in the overall picture. And this is the idea of differential privacy. So you retain the big picture, but you protect the individual data points. And how is that done? As I mentioned, we are utilizing randomness. So we are protecting the individual data points by adding statistical noise. Here is an example which has been used for many years in social science. It's called randomized response, just to illustrate the concept. So we are asking a very sensitive question. We want to find out about tax compliance, for example. So we ask participants if they ever have evaded taxes. Under a normal setting, you can imagine you would not get too many honest answers for obvious reasons. But we can do the experiment in a way which guarantees privacy for the individual, but still enables to get overall insights. So we would ask participants to flip a coin. If the result is tails, they provide a true answer. If the result is heads, they flip the coin for a second time, and then they give a random answer. So, which means every participant has plausible deniability. They can always argue, even if the tax investigation seizes the results with their names and the answers, they can always argue that their answer was the result of a coin flip. But on the other hand, if, for example, 34% of the audience respond yes, I have evaded taxes, then it's relatively easy, straightforward to calculate the actual percentage of tax evaders in the population. In real applications of differential privacy, of course, there are no coins flipped anymore. It's included in the tools that we use. For example, Apple is using it, Google is using it, also Microsoft is using it. If you think about Windows 10 diagnostic data, this is how we protect individual data points before the data is transmitted to Microsoft for further analysis of the data. If you are interested in the concept of differential privacy, I have prepared a white paper which is focused on enterprise audiences. The issue with differential privacy, since it has such a strong research background, many publications are relatively academic, so relatively complicated to understand. This here is really for practitioners, for machine learning practitioners, applying it in enterprise settings. It includes two parts. One part is really explaining the concept and the idea, and then there are a couple of demo notebooks which you can use to really play with the concept, experience it, and also adapt it to your own use cases. And I would like to show one of the examples that we have here in our interactive demo notebooks, so you get an idea how the concept works. So let's assume we are hospital representatives. We have a lot of data, medical data about our patients, and we want to provide these data points for research to develop better medicine, for example. So we have two approaches. The classical approach would be to do data anonymization. So we remove the names, we coarsen the data a little bit, and then hope that it is safe. On the other hand, we can also use differential privacy. We basically convert the original data set in a differentially private data set to protect the data points. And what I would like to do now is to do an actual attack on these two approaches to compare their effectiveness. So we have an adversary, we have an attacker. He or she has some, let's say, telephone book level information about the individuals. In reality, attackers would be able to leverage much more information. And then we have two attacks we will see on the left-hand side, whether if it's possible to re-identify individuals from the anonymized data set, and also if that's also possible with differential privacy. So what you can see here is one example from the, from the interactive demo notebooks. It's a two-pass approach. One is to try to re-identify individuals, and in the second pass, we actually validate the hit rate of the attacker. And what you can see here is that for this data set, it's obviously based on random data, so these are obviously no real patients. We have 30,000 records in total, and based on this relatively simple attack, it's a toy example, the attacker was able to identify almost 1/3 of all individuals, and you can see the result here in this table. And the question is, can we do better? So can we use differential privacy to get better results, so protect the identities more effectively? And this can be seen here in the second attack. So hope the animation works now. So we are doing the attack again, spiced up the animation a little bit because there's actually not too much to see. But if you do it in the notebook, takes 9 minutes, then you can actually see how the attack works. So already we get the indication here that there are 0 potential matches. And actually in this example, the attacker looks quite unhappy. It was actually possible to protect all 30,000 identities. So that is good. So the attacker was not successful. So we were able to protect all identities. The question is, can we still do useful analysis with this protected data? I mean, that's at the end of the day the goal, of course. So let's find out. What we see here is we compare two distributions, two histograms of the diagnosis data. And what you can see here on the left-hand side, the blue bars is the original data, and the yellow bars is the synthetic data. So we see it's actually possible to still derive useful information, statistical information out of the data. And before we wrap up, this was a very simple use case. It was a univariate analysis The question, of course, is, since we're talking about AI, we're talking about machine learning, the question is this also possible using differential privacy? And if you look at these gigantic networks that we are using today, like GPT-3 with more than 100 billion parameters, the issue is always that the AI models, they tend to memorize individual data points. And so there are risks, of course, that you can reconstruct data points or do membership attacks, like finding out if a particular individual has been part of the training set or not. Or here in this case, it's actually called a model inversion attack, where it was possible to reconstruct a recognizable image of the training data. So on the left-hand side, you see the original training image. On the right-hand side, you see the reproduced image. And this is not a generative model. It's a classifier. It's a face recognition model. And it was still possible to derive the training data out of the model based on this model inversion attack. And the question is, can we also do differential privacy for this AI use cases, machine learning use cases, and also deep learning use cases to protect the data also in deep learning? And what you can see here is a demo that we did with PyTorch Opacus. So Opacus is the extension for the PyTorch deep learning library to do differential privacy. It's a relatively straightforward example, so you can reproduce it by yourself if you're interested. It's a classifier to detect pneumonia in radiographs, relatively straightforward, so 5,500 images. Here on the left-hand side, you see the results, the classification results based in the standard non-private training. So the classifier achieves an accuracy of 96%. And if we are doing the same with differential privacy, because of the noise, the accuracy drops a little bit. So we are losing 4 percentage points, but it's still a useful classifier. And you can actually compensate for this loss in accuracy due to the noise if you can add more data. So if you can add more data, then you can also get back to the original accuracy. Does not work in all cases, depends on the use case, depends on the data set. But I think it's a good example which shows that differential privacy is a real use case, not only for simple analytics like what we've seen with the histograms. It's also possible to protect data with differential privacy for machine learning and also for deep learning, as we have seen here in this use case. So I hope that was an interesting overview about the topic. There is, of course, much more information. If you are interested to take a deeper look, I clearly recommend the white paper and also the demo notebooks. This what you see here, the pneumonia case, it's also included in the demo notebook, so you can play with it and apply it to your own use cases for deep learning.
Thank you very much, Andreas. Really interesting topic. I think we're going to hear a lot about it in the next time. I posted the links to the white paper as well as the GitHub profile with the demo notebooks in the chat. And yeah, I want to ask again, everyone, if you have questions, please post them in the chat now, because now we're going to ask Andreas. I'd like to start. I have 2 important questions, actually. The first one is not really a technical question, but more one of application. This sounds really great, an amazing way to ensure individual privacy. But my question would be, how do you communicate that to the customer and especially to the end user? How do you make sure that an average user who may have very little understanding of machine learning understands that this is actually a mathematically proven way to ensure privacy and make them like trust it and use it, becomes actually useful.
Yeah, that's really actually a very good question, also important question, and I'm not sure if I have a perfect answer. I mean, the good thing is, as you mentioned, and I'm not sure if I mentioned that in the talk, differential privacy, which is different to data anonymization, it really comes with a mathematical guarantee, so you can measure the privacy guarantee which you can provide to the individuals who are represented in the data set. That's the good thing, and you can actually tune the strength. So there is a parameter which is called epsilon, and if you set epsilon to very low values, then you have a lot of noise and you have a very strong privacy guarantee, but you have an impact in accuracy. And on the other hand, you can relax it a little bit to get more accurate results, but then the privacy risk might be a little bit higher. Your question, as I understand, is, well, that's nice. How communicate that to end users? I think there is a couple of things you can do. There is an important comparison between the differential privacy scenario and the what is called opt-out scenario. So consider, Fabian, you are thinking about participating in a medical study. What I can do if I use differential privacy, I can tell you, well, there are two scenarios. One scenario is that you do not participate at all, so your record is not included, which is called opt-out scenario, and probably you will feel very safe about that scenario because your data isn't there. And then there is the scenario of differential privacy where your data point is in the data set, but it's protected with differential privacy. And the promise, what you can give to an individual is to say the risk of any privacy leakage is essentially the same. So there is no practical difference between this opt-out scenario and the scenario where we protect your record using differential privacy. I think this would be a very strong statement and relatively straightforward to understand. If you want to go a little bit further, you can actually use case specific these parameters to try to calculate a probability, so the probability of a data leakage. But not everybody is happy with probabilities, but this would also be possible.
Okay, thank you very much. That's really interesting, and I think that's a way to communicate that properly, even to people who are not familiar with machine learning. We have another question here. Harald Henschke asks, in real use cases in which differential privacy anonymization is required and is implemented, who decides whether the level of protection is sufficient in, for example, Germany or the European Union?
As I understand, there are laws which define the level of data protection, but they are typically not specific enough so that you can really derive from the language, from how the law is formulated, that, for example, data anonymization with a K of 5, so 5 anonymization or 10 anonymization is sufficient. If you translate this to differential privacy, you won't find any specific language. So you can say, okay, if we use an epsilon of 2, so the differential privacy parameter, then it's fine. I think this has to come from practice. Typically, if we are talking about pseudonymization and anonymization, my experience is that regulators, so regulatory bodies, could help to really find out or give guidance if this parameter it is sufficient. So I don't think that you can directly derive it from the language of the law, but just work with data privacy experts, work with regulators, and then find out if a specific proposal, which includes differential privacy and other measures, is sufficient, but it will always be use case specific. So there is some guidance in the literature how to set the parameters for differential privacy, so epsilon for specific use cases, but this is more a recommendation, and I would approach it making some suggestions for the use case and then work with a regulator to find out if they can live with that level or not. Maybe one final comment. There is a very strong lighthouse use case, which is the US census. So the publishing of the 2020 census results will be based on differential privacy for the first time. And I think this gets the discussion around that, and also the way the Census Bureau chose the parameters, the privacy guarantee, would also be a very interesting discussion to follow. But I think it will always be use case specific.
That's really interesting. Like, where could we find more information on that lighthouse?
The Census Bureau is a quite famous example. If you just use Google or Bing to find out, it's the U.S. Census Bureau, and it's the 2020 census, the publication of results. And there is a lot of discussions going on. For example, what's the impact of the noise? Is it possible that small communities will disappear in the statistics? That's really an interesting discussion. I mean, there are a lot of use cases already implemented by the big tech players, as I mentioned, Google, Apple, and also Microsoft, and you can find examples. So we have discussed on YouTube, for example, how we protect Windows 10 diagnostic data using differential privacy, but you can find also very vibrant discussion about the US Census discussion, and it's really interesting.
Okay, we have to come to an end now, sadly. Our time is almost over. Big thank you to everyone for participating in this use case, and of course, most important to our speaker, Andreas, for this amazing presentation. I think it's safe to say that this is a topic we are going to hear a lot about in the near future. And last but not least, let me quickly announce datalift number 5 on May the 28th. We would be delighted to have you again. I'm going to post the link into the chat. Yeah, and thank you everyone. Goodbye. Have a nice day.
Thank you.